Hey guys, I'm Ms. Peterson, and welcome to your AP Chemistry Lecture 1-1, all about understanding matter. In this lecture, we're going to be talking about states of matter, classifications, really working on the terminology that chemists use to define matter. We'll talk about physical and chemical properties and also percent composition. In our textbook, this is sections 1.1, 1.2, and 1.3. From the AP Chemistry curriculum based on the College Board, this lecture covers topics 1.3, elemental composition of pure substances, and 1.4, composition of mixtures. We'll also be doing a lab video that is related to this lecture. So first, I just want to talk about the states of matter. This is probably a review. Which state of matter has a rigid shape? Okay, well, we know that that is our solids. The fixed volume, that's going to be our liquids, and our gases are the ones that have the volume that changes to fill the container. Note, both liquids and gases are fluids. Okay, gases are also considered a fluid. And what that means is that they change in response to their environment. Okay, for both the liquids and gases, you're going to see a lot more variation with temperature and pressure, where solids have very little change in volume in response to temperature and pressure. And that's one of those big distinguishing things. Okay, so how do chemists distinguish between different types of matter? This is the vocabulary that we're going to be using throughout this course. So when we refer to matter, that is the stuff, okay? Everything's matter. Now, you guys might have learned from middle school that atoms are the building block of matter, okay? All matter is made of atoms. Atoms are made of protons, neutrons, electrons, etc., okay? Now, if you have only one type of atom, for example, say in this sample, I don't have anything available, but in this sample, all of the atoms are the same. They all contain 6 protons in them. Then you have a sample of carbon, and that is an element. Okay? If it's not found on the periodic table, it's not an element. Okay? Composed of a single type of atom. Note, though, that elements can also be they can be things like magnesium or calcium, but they can also be what's called diatomics. H2 is still an element because they're all hydrogen atoms. All of the atoms are the same. Same for O2 and any other natural element that tends to bind to itself. Okay? Even though it's a compound, next vocab word there, it is still an element. Okay? So, if those atoms, when they bond together, if they share their electrons, this is a covalent compound, then it is a molecule. Now, a common mistake people will make is confusing those words molecule and compound. Compound is more general. If you got two things bonded together, it's a compound. Where molecule have to be bonded together through sharing electrons. Okay, so these are covalent. An example is water. Okay, water is a molecule. Sodium chloride is not. Okay, that is an ionic compound. It is not a molecule. They bond because of the attraction between their atoms, because they are ions. They are not molecules. Okay. Now, if you are unsure about which of these words to use, your default go-to is going to be particle. Okay? A particle can mean a molecule, a compound, an element, an ion. Okay? It can be any single unit of a substance. So if you're looking for a more general term, we tend to use particle. Okay? So you can kind of see down here, you can have atoms of an element, they're all the same. Molecules of an element, they are bonded together. Molecules of a compound, okay, you got the different types of atoms bonded together, or a mixture of elements and compounds. Okay, all work out. So now we need to talk about the properties, aka the characteristics of a substance. And those are kind of divided into two broad categories in chemistry. Your physical properties, those are the properties of your lone sample, okay? Mass, volume, boiling temperature, melting temperature, color, shape, size, okay? Those are all physical properties. And physical properties could be extensive that depend on the amount of a substance. So what are some examples of properties that might change depending on how much you have? Well, mass, okay, volume, shape, okay? Shape is something that could change very easily. However, is the density of gold going to change whether you have a small ring of gold or a big chunky necklace of gold? No. Okay, density is what we call an intensive property. Now, intensive properties are independent of the amount. If you have gold, it is always going to be 19.33 grams per milliliter. Okay, if you have water, it is always going to boil at 100 degrees Celsius. It might take longer to heat up that larger pot, but once it reaches that temperature, it's going to boil, whether it's a small cup or a big pot. Other intensive properties can be things like color, or we'll talk about hardness for some chemicals. Things like that are intensive properties. Okay, so we need to get some equations written down here. Now, whenever I have these boxes, that refers to something that is on your AP Chemistry reference table. This is your reference table that you'll get on the exam. And if we go back here to gases, liquids, and solids, we see some of these chemical equations that we're already talking about. For example, density equals mass over volume. Go ahead and label those variables. We have density equals mass over volume. Now, the typical units for that, I'm going to write in a different color. Density will often use grams per milliliter, so then our mass would be in grams and our volume would be in milliliters. And note that a milliliter is also equal to a cubic centimeter, so those are often used interchangeably in chemistry. Okay, a cubic centimeter is the same as a milliliter. One of the other wonderful ways that the metric system was organized. Okay, which brings us to another property. Okay, this is an intensive property, but it's one that changes all the time. It depends just about that sample that you're talking about right at that moment. And it's the measure of the average kinetic energy of the molecules, aka it's temperature. Okay, now temperature is directly proportional to kinetic energy. That's what this little fishy sign means, directly proportional to. However, the actual equation that relates energy to temperature changes based on what molecule, what atom, what substance you were talking about. So we don't need to know that equation. We do need to know that kinetic energy is equal to 1/2 mv squared. Okay, and this is for when you're talking about the kinetic energy of a single molecule. Okay, why it says molecule on your equation sheet and not atom or particle or a more general term, I don't know, because this applies to all of them. But that is a thing that we need to know. So we have kinetic energy. 1/2, this is our mass, and then v squared is the velocity of the particles. So note that it is a lowercase v here and an uppercase v in our density. So lowercase v is for velocity, uppercase v is going to be for volume. Now, the typical units of that would be joules for energy, kilograms for mass, and then meters per second for velocity. Okay? So if I were to double the speed of all of the molecules, okay, so if the velocity doubles, what would happen to the temperature? Okay, well, the velocity is squared in the equation. So the kinetic energy would be times 4, which therefore mean the temperature would be 4 times as much as it was. That's a question that comes up all the time in AP Chem. But as long as you can just look at that equation for kinetic energy and relate those two and know that temperature is directly proportional to kinetic energy, you'll be good to go. There are some things in chemistry that we should have memorized, and one of them, I'm just double checking that it's not on your equation sheet, and nope, it is not. One of them is the freezing point and the boiling point of water. Because we use water all the time in chemistry, we need to have those things memorized. So in Celsius, which is what we're going to use, we're not going to use Fahrenheit, 0 degrees Celsius is the freezing point of water, and the melting point, which is also the boiling point, okay, basically the temperature that it can go from a liquid to a gas or from a gas to a liquid, is 100 degrees Celsius. Easy, because water is what the Celsius temperature scale was based on. Now, another temperature scale that we'll use in chemistry on equation pretty often is Kelvin. Now, Kelvin was based on the motion of molecules. Okay, it isn't what we call an absolute temperature scale, so it is only positive. If you're at 0 Kelvin, that is called absolute zero. And that means that the particles are not moving anymore. This is super applicable when you get into like the physics of the really small, because it's a lot easier to study something if it's moving slower. And while we can't get to 0 Kelvin, we have gotten pretty close. There's a really cool documentary called The Quest for Cold from Nova that I highly recommend watching. So we do need to know that conversion from Kelvin to Celsius. You'll end up memorizing it eventually, but it's also on your equation sheet in that same area, solids, liquids, and gases. And it's that Kelvin equals degrees Celsius plus 273. Okay, technically it's 273.15, oops. But if you just use 273, you're going to be good to go for the majority of applications. Okay, so again, that one was the temperature in Kelvin, and converting it to Celsius, you just add 173. Okay, Celsius, add 173. If you're at Kelvin, you subtract 273 to get to Celsius. And I recognize I just said 173. I'm sorry, 273. Okay, cool. Okay, cool. So those are physical properties. Now let's talk about chemical properties. All chemical properties is how it reacts with other substances. Okay, so we're going to go through this description and highlight the chemical properties. We'll go ahead and do the chemical properties first, since that's the box that we're on. I will highlight the chemical properties in this pretty aqua color. So zinc is a silver gray colored metal that melts at 420 degrees Celsius. When they're added to dilute, we're talking about chemicals. Hydrogen is given off and the metal dissolves. That's a description of what it does chemically. So it's a chemical property. It also reacts slowly with oxygen gas to form zinc oxide. That is a chemical property. Where the physical properties, go ahead and do those. That orange is kind of hard to see. Let me just do yellow. The physical properties are things that describe it. It's a silver gray colored metal. It melts at 420 degrees Celsius. It has a hardness of 2.5 on the Mohs scale and a density of that at that temperature. Those are all of its physical properties. Bonus points. Which of the physical properties are intensive, which we'll mark with an I, or extensive, which we'll mark with an E? Well, color. Does color change whether you have a lot of it or a little of it? No, it's going to be the same color. So that is an intensive property. Okay? Intensive properties are independent of the amount. Where melting temperature, same. Intensive property. Hardness is an intensive property, and density is an intensive property. An extensive property, there weren't any given in here, but extensive, if they would have given us the mass of the sample, or the volume of the sample or anything like that, that could have been an example of an extensive property. But all the ones that they described were intensive. Okay, cool? Okay, cool. Now, let's move on and talk about how we separate chemicals, okay, and mixtures. So, that depends. Sometimes it's really easy. Like, can you guys think for a second, how would you separate iron filings from copper filings, okay? Well, you guys might know that iron is magnetic, while copper is not. So you could use a magnet. You're separating them based on the properties that they have. And that's what all of separation is. There are a couple common methods that we'll talk about in more detail. Filtration, okay, is think about your coffee filter. You pour the water through the coffee, some of that coffee flavor goes through the filter, the coffee solid stays on the filter. Easy. Distillation, okay, this is a picture of a distillation apparatus for separating sodium chloride solution from its components. So basically, if you wanted to boil off water, you can vaporize the water will condense, and then is received here. It has a condenser, which is just a big tube filled with cold water with like the small tube for the vapor to run through it. So as it runs through, it cools down and becomes back into a liquid. And then after the water is boiled away, the pure sodium chloride remains. Okay? They also use this to separate different components of things like oil, so that you get just the components that you want for your gasoline. Okay? You can separate it based on their different boiling points. Chromatography is another mixture that we will see a couple times in this course. Basically, you're separating things by their ability to bond and adhere to different surfaces. There's column chromatography and paper chromatography and gas chromatography and liquid chromatography and all of these different ways of doing it. But basically, it's just letting things separate, because if you have, say, a solvent here, they're going to be absorbed through different degrees as it passes through those filters. Normally that's like sand or beads of some sort. There could be different levels of that, but they're going to move at different speeds and thus separate. One of the funnest, these separation labs, the funnest labs that you'll get to do in college chemistry. Okay, so last thing we're going to talk about in this lecture is how do we quantitatively describe the compounds. And the most common way that we'll do in this class is percent composition by mass. So percentage, you guys probably know to get to the percent, it's always the part over the whole times 100 to get it in percent form. Now we'll often be doing mass percentages. You can also find percent by volume. That is a common one that you'll see. Okay. So let's compare and contrast two compounds, methanol, CH3OH, and sucrose, carbon, hydrogen, atom. Carbon, C12H22O11, aka sucrose. So these are both a compound formed from carbon, hydrogen, and oxygen atoms. And so is sucrose. They're both compounds formed by carbon, hydrogen, and oxygen atoms. Now, most organic compounds are compounds formed by carbon, hydrogen, and oxygen atoms, and some nitrogen. So this is what they have in common. But methanol is a non-drinking alcohol. It's used to make like cleaners and solvents and stuff like that. And sucrose is table sugar. Okay, so these are very different compounds chemically because of what they're made of. And we could go ahead and look at their mass percentages to figure out kind of a little bit more difference between them. So if we have, I'm going to rewrite this as CH4O just for purposes of finding my molar mass. So I have a carbon, got my calculator here. Carbon has a mass of 12.01. Hydrogen, we have 4 of them, times the mass of a hydrogen atom, which is 1.01. All these masses just coming from the periodic table. And then oxygen, which is 16.00. So the whole of a molecule of methanol is 32.05 grams per mole. Okay, now for sucrose, if you find its molar mass, we have 12.01 times 12, 1.01 times 22, 16.00 times 11. That gives us 342.34 grams per mole. Okay, so you can see that the sucrose is about 10 times heavier or by mass than the carbon. And let's go ahead and figure out the mass percentages of these just so that we can get some practice with that. So carbon, we have 1 carbon. We're going to find all of them. The percent by mass. Percent by mass. And we'll see how similar these look when you look at it this way. Okay, so for carbon, we only have 1, so we would have 12.01 over 32.05, and then we times it by 100. So methanol is 37% carbon. It is, we have 4 hydrogens, so that's going to be 4 times 1.01 over the whole, 32.05. And we have about 12.6, I'm just going to round and say 13% hydrogen. And then it is, I'm already seeing that this is about half, okay, about 50%, which, I mean, we could also just subtract from 100, okay, and we get 49.9 or 50% oxygen. Okay, let's go ahead and do the same thing, but for sucrose. So we have 12 times 12.01 over the whole, 342.34, and then times it by 100 to get it in percent form, 22.22, 2 times 22 times 1.01 over 342.34, and oxygen, and now let me plug all of those into my calculator. So this one is about 42% carbon. And about 6% hydrogen. And about 51% oxygen. So both of these compounds are about 50% oxygen, but the sucrose has a much lower percentage of hydrogen. Fun fact, this is also, it's all those hydrogens that determine the saturation of fats. So if you ever see on a food label saturated fat versus unsaturated fat, what it's saturated with is hydrogen. So the saturated fats have a lot higher mass percentage of hydrogen than other fats. Okay, cool? Okay, cool. Let's do some practice problems. So our first practice problem is going to be to calculate the percent composition of each element in calcium nitrate, which is CaNO3. So the first thing I'm going to do is I'm going to find the molar mass, or the mass of one particle of calcium nitrate. So we have calcium atoms, we have nitrogen atoms, and we have oxygen atoms. We have one calcium, and then that 2 distributes in, so that we have 2 nitrogens and 2 times 3, 6 oxygens. The mass of calcium, and again, I'm just getting these directly from the periodic table, is 40.08. Nitrogen is 14.01, and oxygen is 16.00. So the mass of calcium is 40.08, nitrogen 28.02, and oxygen 96.00. Okay, that is how many grams we have per mole of each of those compounds. So when we add them all up, we get that the molar mass of it is I can math. I actually can't math. 164.1 grams per mole. Okay. So the reason that I had these there is now it makes it really easy for me to do my mass percents. Okay. So I'll go ahead and swap to another color to get the percentages. So we have calcium, which is going to be 40.08 over 164.1, and then we times it by 100 to get it in the right form. So it's about 24.4%. Nitrogen, I'm not going to show the work, but it's 28.02 divided by 164.1. So we have 17.1%. And then the oxygen should be, okay, we have 24 and 17, so a little over, should be about 50. This is why I have a calculator. I am not good at doing math in my head. I wish I was better at it. I should do some exercises on that. 58.5% oxygen. Okay, cool. Okay, cool. Last example problem. A student is doing an experiment to determine the salinity, salt composition of a sample of ocean water. Assuming that sodium chloride is the only salt present, it's not quite true, but it's like a very large, over 90%. In the experiment, she collects 10 milliliters of water on a hot day from various locations. So which separation would work? Well, the easiest separation would be to do a distillation. Okay, boil off the water. Okay, so she performs that separation on the 10 milliliters of water, and we have the density of water, and collects 0.38 grams of salt. What is the percent composition of salt water in the ocean? Okay, so we know how much salt we have, but we don't know the mass of the original sample, but we know its density, so we can find that pretty easily. We have 10.0 milliliters, okay, and then we're just going to times it by 1.03 grams per milliliter, and we get that the original sample had a mass of 10.3 grams. So to figure out our percent then, it is just going to be the salt, 0.38 grams of salt over the whole sample, which was 10.3 grams, times it by 100 in order to get it in percent form. And we get that that sample was 3.69% salt. Okay? Now, let's talk about some sources of error when doing this. Okay? That is a little highly salty. She wasn't expecting to get that high a number. Some possible sources would be not drying it completely, or there's still some water there, which contributes to that mass. Another problem is going to be those impurities, that it is not pure salt water. That is definitely going to be one of the sources of error. But those will kind of be our two main ones. What we don't want to say for sources of error on this is she might have spilled some. Okay? We're hoping that if you spilled something, you would redo the experiment. So those kinds of errors aren't really sources of error that would show up in a lab type environment. And that's it for today. Do you understand matter better? Kind of understand percent composition? Okay, cool. Okay, cool.